Hello friends, welcome to today's session from School of Sciences. I'm Dr. Sanjeev Kumar, Professor in Physical Chemistry. In today's session, I'll take up Introduction to Wave Mechanics. This is a formalism which is used to understand the behavior of microscopic particles like atoms and molecules. The session is planned as follows. That is, to begin with, I'll briefly recall what we learned earlier about Bohr's model of atom and its inadequacy. In what way was it not good enough? Thereafter, I'll take up two consequences of the quantum mechanical nature of atoms and molecules, which are very, very pertinent to understand the behavior of atoms and molecules at a later stage, so that we can have a real look at the modern look at, so to say, about the structure of atom. And then we will try to make a case for it, try to argue out that why do we need something called as a wave mechanics? Why do we need new kind of a theory for that? Thereafter, I'll come down to the main theme of today's session, that is what is called as wave mechanics. Wave mechanics is nothing but a formalism which is used to understand the behavior of atoms and molecules, as I just mentioned before. And then towards the end, I'll try to sum up what we do in today's session. Okay, let's try to make a beginning and recall what we learned earlier about Bohr's model of atom. You know from your earlier studies also, that is, according to Bohr's model of atom, basically what we have a nucleus in the center, then the electron is moving around the nucleus in circular paths, what is called as orbits over there. As I just mentioned here, that we have a nucleus in the center, there are circular orbits where the electron can move around, and these orbits actually, it's not that electron can take up any orbit it wishes to, there are certain restrictions on that. That means these orbits are quantized. It can take up only certain orbits around the nucleus. And further, one more very important kind of aspect of Bohr's model is that as long as the electron is in a given orbit, its energy doesn't change, which is very, very strong kind of a proposition from Bohr, because according to classical mechanics, any charged particle moving around a charged system must radiate energy. And Bohr proposed that it doesn't happen so, that it stays to be constant over there. That's why these orbits wherein the electron moves around the nucleus, they are called as stationary states. Going further, we also know from Bohr's model that the electron in an orbit can take up energy and go to higher energy orbit, or it can go from a higher level to a lower level by emitting radiation there. So there can be transitions amongst the energy levels either by absorption or by emission of radiation there. And also we know that electrons' orbital angular momentum is quantized. So they are the basic premises of Bohr's atomic theory, so to say. I'm sure that you understand that for any model of atom to be acceptable, the first and foremost requirement is that this must account for the spectrum of hydrogen atom. And when we try to put Bohr's model as a test against this hydrogen atom spectrum, let's see what do we get here. What do we get is that the energy level diagram what we have, the transition amongst these energy levels, that means the transition from a higher energy level to a lower one there, and these all can have been found to be in excellent agreement with what is experimentally observed in the so-called Lyman series, Balmer series, and so on and so forth there. That means Bohr's model was perfectly in agreement with experimental observations as regards the hydrogen atom spectrum. So to that extent, Bohr's model was acceptable. It actually proved to be very, very successful as against the previous model, that is Rutherford's model over there. But if we try to really critically analyze Bohr's model, what we find is that, okay, it accounts for the stability of atom and also for the spectrum of hydrogen atom, as I just mentioned here, but it doesn't explain the spectra for multi-electron systems. That means if I have a system, say a helium atom or a lithium atom, where there are more than one electron is there, then this Bohr's model is not good enough, because the spectrum there is not explainable on the basis of Bohr's model there. And also, it doesn't explain so-called Zeeman and Stark's effect, that is the observation of extra lines in electrical and magnetic fields over there. Also, there was no justification, so to say, for the stationary states or the kind of quantization of orbital angular momentum for the electron in the atom there. So on these counts, so what we find is from this kind of analysis that Bohr's model had a partial success, because it was good enough, or rather very, very good in terms of explaining the spectrum of hydrogen atom, but on other counts like Zeeman effect, Stark effect, and multi-electron systems and all, it was not good enough for a matter. So essentially, something more is required over there. But before we come to that something more, let's talk about two more important things over there, what is called as the consequences of quantum mechanical nature. Because typically what we do is we deal with systems which are observable, we can see with the naked eyes, macroscopic systems. Say a car moving, a particle is moving around there, or maybe we can think of a cosmic bodies there, sun, moon, things like that. So all these things, the behavior of them all can be explained fairly well in terms of classical mechanics. But when we come down to microscopic systems like atoms, molecules, and things like that, we find that these so-called classical laws do not hold well over there. And that means the systems which are microscopic, like atoms and molecules, they behave very, very differently from our macroscopic systems. Macro means large systems there. Now, if they are behaving differently, what are the two important consequences which are specific to the quantum mechanical systems? Let's look at them. Let's look at the first one first. And that happens to be de Broglie's idea of matter waves there. I'm sure that you recall from your earlier studies that light has dual character. It can behave as particle or as waves. De Broglie actually extended that argument from light or radiation to matter and suggested that the particles like electron should also have wave character there. That means they also should have duality of nature there. That means they should be, because typically we know that electrons behave like particles. But de Broglie suggested that this, though okay, it's acceptable that electron does behave as particles sometimes, but it should also have an associated wave character. And accordingly, he proposed that lambda to be equal to h by p. That is, the associated wave character can be given in terms of a wavelength for the electron there. And this actually was established experimentally by Thomson and Germer. So what do we have is, de Broglie proposed that lambda should be equal to h by p. That is, this is basically an expression for the wavelength of which is associated with a moving electron or a moving particle of that size. And then this behavior of electron was confirmed by Thomson and Germer in terms of diffraction of electron beam for that matter. Because basically what we understand from diffraction is that we know that solid materials, say crystals, they diffract X-ray radiation, X-rays. So we have what's called as X-ray diffraction pattern there. So X-ray diffraction is happening because the wavelength of X-rays is kind of similar to what we have in case of the interelectronic or interatomic distances between different species in the crystal over there. Similar to that, what was done is that you take an electron beam, accelerated enough in such a fashion that they have a wavelength which is comparable to the interatomic or interionic distances between a crystal, and then we try to see does it diffract or not. It was found that the electron beam could be diffracted, and that actually led to the formulation of what's called as a electron diffraction, a phenomenon which we extensively use nowadays there. Okay, so de Broglie suggested that there should be a wave character to electron, and that was established experimentally by Thomson and Germer. And if this be so, what is the implication of this behavior? The implication is that any model of atom we talk about, this must accommodate the wave character of electron. Because Bohr model suggests me that electron is moving around the nucleus in form of in a circular path called as an orbit there. Essentially, it is visualizing electron to be a particle. But de Broglie suggested it must also have a wave character there. So implication is that the wave character of electron must be accounted for there. Okay, let's look at second consequence of quantization, what's called as Heisenberg's uncertainty principle. I'm sure that we all know about it because that's what you learned at your school as well. That is, Heisenberg's uncertainty principle states that it is impossible simultaneously to determine the position and momentum of an object with certainty. That is, what do we have? So an expression like delta x into delta p to be greater than or equal to h by 4 pi, where delta x happens to be the uncertainty in the position of the particle and delta p is uncertainty into the momentum of the particle there, and that is must be equal to or greater than h by 4 pi. Okay, so if this be so, the implication is that we can only talk about the probabilities of finding the electron and its momentum. We cannot talk about the position or the momentum of electron with certainty over there. And the implication further goes as follows. That is, we can only talk about kind of probabilities. You can see it here. So this shows that this is a path which is a well-defined path over there. The Heisenberg suggests that this is not possible to do for systems like atoms and molecules. We can only talk about the probability of finding electron. So that is the implication of Heisenberg's uncertainty principle. Okay, so where are we? Where are we? We talked about Bohr's model and found that it is inadequate. And then also we have talked about two consequences of the quantum mechanical nature of atoms and molecules, and the consequences happen to be the duality, that is the particle must have a wave character, and also uncertainty principle there. Let's now try to put our Bohr's model to test in the light of these two observations there. If I try to critically revisit Bohr's model, we find that Bohr's model doesn't consider the wave character of electron, number one. Number two, it proposes definite path with well-defined position and velocities, which again is not acceptable because Heisenberg suggests we cannot talk about the certainties. We can't talk about the definite paths over there. We can only talk about the probabilities there. So essentially, in the light of this, we find that our Bohr's model doesn't accommodate either the de Broglie's formalism or the ideas over there, or Heisenberg's uncertainty principle there. That means on both these counts, we find that Bohr's model happens to be inadequate. That actually lets us to suggest that we need a new theory. And that theory actually happens to be the wave mechanics. So essentially what I've done so far is I've tried to establish the need for a new theory to accommodate or to account for the nature, or to describe the nature of particles like electrons and molecules over there. Okay, now what is this wave mechanics? Let's understand this now. Wave mechanics basically is a mathematical approach that is used to understand the behavior of microscopic particles, which I've been talking again and again about atoms and molecules over there. And essentially, this actually accommodates the two big inadequacies of Bohr's model. That is, it does bring in the ideas of de Broglie, that is, it's called as wave mechanics. That means it is inherent on that we're going to talk about the wave nature of electron, number one. And also, we will find later on that it does intrinsically accommodate Heisenberg's principle as well over there. So, essentially, next step is that we understand what is this wave mechanics. As I just mentioned, wave mechanics is a mathematical approach or mathematical formalism to understand quantum mechanical systems like atoms and molecules. And this system was actually, this theory for the matter, was proposed by Schrodinger in 1925. And this theory basically is based on certain set of postulates. And the postulates, what I'm going to do now is I'm going to talk to you about these postulates in a very, very simplistic way. So I just give you some essence of what exactly these postulates are, what is the significance of them, and then how do we deal with a quantum mechanical system in the light of these postulates over there. If we go further and look at the first postulate, the very first postulate, I'm sure that you understand what is a postulate. Postulate is some set of rules over there, because typically what happens is, I'm sure that you have played some board games at home. When you, as a child, when you play a game, so that you play the game with certain set of rules over there. Maybe if I throw a dice, if 6 comes, I can move further. If 6 doesn't come, I have to hold back. Okay, so some set of rules are there. So we play the game with a set of rules over there, and then follow the rule and enjoy the game. Similarly, in wave mechanics also, there are certain set of rules called as postulates there. What I'm going to do now is I'm going to talk about those postulates one by one, and then we will see how do we use these postulates to understand simple systems. We will talk about systems in the next session over there. Okay, let's look at the first rule or the first postulate. First postulate states that the behavior of a single particle is described as fully as possible in terms of a wave function. Okay, what does it mean? What does it mean is that the very first, as we said, that wave mechanics kind of involves or is based on the idea of de Broglie, that is, there has to be a wave character to electron. So that wave character of electron is assigned in terms of something called as a wave function. That's the first postulate. The first rule of the game says that is the behavior of the particle will be described as fully as possible in terms of something called as a wave function psi, which we denote as psi. And then this psi actually contains all the information about the particle. So I'm talking about electron moving in a atom there. So how does the electron behave where is it, how much of, what's the possibility of it to be there, what is the energy of it, what's the momentum of that. All that information is contained into this single parameter called as psi of the wave function. So that is a very, very crucial thing over there. But the question comes is, if I have this psi, how do I get this psi for a given system? And that is given by what is called as my second postulate. Before we come to second postulate, let me just try to give you a little more information about, because we said that this psi contains all the information about a system, but there are certain kind of qualifications which the wave function has to meet, because I cannot take any function and say this is going to be my wave function. I had to have certain criteria for that, and that criteria, let's talk about that first before we come to the second postulate. And that criteria happens to be wave function which is there, which has all the information about the system, must have certain properties like this must be single valued. I'll explain the meaning of all this. Single valued, then it has to be continuous, then it must be finite, this must be smoothly varying, and also it must vanish at the boundaries. So these are 5 kind of criteria which the wave function must meet. Let's look at some functions, some wave functions. I give you a pictorial representation of that, which actually are not acceptable wave functions there. Let's look at this picture. The first function here, you see that it is not single valued. What does it mean? If I look at on x-axis at this value x1, we find that this function, whatever this function is, has got 1, 2, or 3 different values there. That means it is not a single valued function. So such functions are not acceptable. This is one function which is poorly behaving, because it's not acceptable wave function to me. And second one is this one, which is not continuous. What does it mean? If I look at this, it starts from here, goes like this. At somewhere x1, there's a discontinuity over there, because this breaks down over there, then starts from here and then behaves this particular way. This is again not a acceptable wave function, because it is not continuous. So a wave function must be single valued, continuous, and also it must be finite. This actually is a representation of a function which is not finite. We can find that at x1 and x2, this function goes to infinity. Such function also is not acceptable there. And then look at this last one here. We find that this is not smoothly varying. Smoothly varying is, it should be going smoothly over there. What I will find is that at this point that there is a discontinuity coming over there. That means there's kind of a sudden change in the slope is there. It's not smooth. Such functions are not acceptable over there. Okay, let's move further and talk about the second postulate now. Second postulate says this wave function which we're talking about can be obtained by solving what is called as a Schrodinger wave equation, and we simply can put it as h psi to be equal to E psi. And where h happens to be an operator for total energy. We'll talk more about it when we move further. And then one more thing we have to understand here is this Schrodinger wave equation is a special kind of an equation wherein the function psi is called as an eigenfunction, the operator is called as eigenoperator, and this constant here or eigenvalue, and this equation, as I mentioned earlier, is called as Eigen Equation. What you find is that in this case, the operator h operates over the function, gives the function back multiplied by a constant over there. So this is a very typical kind of an equation what's called as a Eigen Equation. Let's move further and talk about the third postulate. First postulate says there will be something called as psi, which has all the information about system. Second postulate tells me that I can get this psi by solving Schrodinger wave equation. And the third postulate tells me that how do I get information from this wave function psi. And that postulate reads as the information available in the wave function can be obtained by using a suitable quantum mechanical operator or for that particular property over there. What it means is the following. That is, if I have got psi, I can operate it over by a function, kind of an operator A. When I operate over this, I get the function psi back and I get a constant here. So this is the measurable value of that particular property. What it means is, suppose I've got a wave function psi and I want to find out what is the momentum of the particle there. So I take the operator for momentum, operate over the function, get the value of momentum there. So it is like this. Okay. And then let's look at some operators which are used here. This for position. This is for position along x-axis, y-axis, and so on and so forth. These are the momentum operators over there. And then the fourth postulate actually tries to ascribe some kind of a meaning to psi, which it says is the square of the wave function, psi square, gives me a measure of the probability. And we look at this expression here, psi square, we put it as psi into psi star, and psi star is nothing but the complex conjugate of the wave function. Sometimes the function can be complex, so we have to talk about use the complex conjugate over there so that we get a real value from there. So essentially what we have seen is that we were talking about why do we need wave mechanics, and then what is wave mechanics? Wave mechanics is a formalism which is used to understand, which can be used to understand the behavior of particles like atoms and molecules, and it is based on certain postulates. First postulate tells me that there has to be something called as a wave function psi, which contains all the information about the system, number one. Number two tells me that this wave function I can obtain by solving a wave equation called as Schrodinger wave equation, which reads as h psi is equal to e psi, where h happens to be an operator called as Hamiltonian there. And the third postulate gives me a way or the mechanism to get information out from the wave function psi. For that, we use a suitable operator over there called as quantum mechanical operator for the property in question. And the fourth postulate gives some kind of a meaning to psi. That is, the square of wave function gives me a measure of probability, and psi square actually is called as probability density. We'll talk more about it as we move further. Okay, let's sum up what we did today. What basically we did today is we started by talking about Bohr's model and try to critically analyze that, and found that Bohr model was good enough to explain the spectrum of hydrogen atom, but it was inadequate in number of other aspects over there. Thereafter, we took up two important consequences of quantum mechanical nature, and then in the process we made a case for need of a new theory, and that theory happened to be wave mechanics. And thereafter we talked about wave mechanics in terms of its postulates. We talked about the meaning of that, and in the next session we will try to see how do we put wave mechanics to use, because essentially we have done why of wave mechanics, then we talked about what is wave mechanics. Now in the next session we'll talk about how of it, how do I use wave mechanics to understand systems which are of quantum mechanical nature. Thank you.